train delayed again? Is the weather to blame? The railway is subjected to all the worst things Mother Nature can throw at it, and sometimes Mother Nature gets the win. From the cold of winter to the heat of summer, each season brings its own challenges, but some definitely more than others. So let's take each season in turn and help you understand why your train could be delayed. Let's start with the cold depths of winter, the season of Christmas, frost, snow and short days. Temperatures drop during the winter, in some places a lot further than others, and this is the root cause of a lot of the issues railway engineers have to deal with. Some of the more sensitive railway equipment, such as signalling relays, are sheltered in line-side cabinets, but rails and other parts are not so lucky. These are the parts of the railway where the majority of the issues occur, which isn't surprising, I know. Let's first look at the equipment that gets power to the electric trains, the overhead line and the less common third rail. Both run along the route of the track, above or next to it. Electricity is transferred from both to the train through surface contact, a pantograph for overhead line and a chute for third rail. In the cold, both the overhead line wire and the conductor rail become great surfaces for ice to gather on. A little dusting is not an issue, but when it builds up into a thick layer, it starts to prevent the contact necessary for the flow of electricity. In the case of the overhead line, lovely icicles can form that can damage the pantograph or drop onto trains once disturbed. While trains are well built and small icicles won't cause any damage, size does matter, so there's always the potential of them growing big enough to cause real issues. When this issue came up on another video I put out on the channel, a number of people helpfully pointed out that icebreakers can be fitted to the pantographs of trains to knock off the icicles, but there's still a limit to what these can deal with. For third rail, the surface of the railhead is flat and large. Icicles are not an issue, but layers of ice can still form on this surface, and the shoe will just run across the top of the ice. With both third rail and overhead line, trains frequently passing through the area help to keep ice from building up, as it is regularly being disturbed. It is on the less frequently used routes and areas that build-up can get to really heavy amounts where icebreakers can struggle. For some areas, ghost trains, which I enter, can be run to prevent the build-up of the ice. This typically happens during the night when no trains would normally run, and when it's obviously the coldest. Anti-icing fluid can also be sprayed onto the third rail to help prevent ice forming. We cannot also forget the running rails. Like the surface of the platform you stand on while waiting for a train, ice makes the surface of the running rails slippery. Unlike car tyres, train wheels are not made of grippy rubber, but of metal. This can lead to some grip issues, especially in freight trains where the loads being pulled are very high. Accelerating from stationary or slowing down are the two risky areas. It can lead to damage to the rail from slipping wheels or trains sliding straight past signals. Sanding is the traditional way wheel grip is improved if needed. Some trains are fitted with equipment that applies a fine layer of dry sand to the railhead, which assists with grip. Before we move on from the issues with ice, I want to nip back to those lovely icicles we touched on earlier. When not forming on the overhead line, another place they can form is the inside of tunnels or the underside of bridges. These are places where water generally works through and drips onto the track, the perfect conditions for icicles to form. Again, the risk is from them dropping onto trains or becoming long enough that trains actually hit them as they pass. Snow is next on the list. Lovely snow. Some parts of the world get a lot of it and are well set up for it. Others not so much. A light dusting of snow in the UK and the place generally comes to a standstill. Snow brings slightly different problems to ice. It's cold weather friend. If it is falling, there is the visibility issue that anyone who has driven a car while it's snowing, especially at night, will be familiar with. Train drivers need to see signals, stopping points at platforms, and most importantly, be sure that the line ahead of them is clear. Reduced visibility means running at a reduced speed. If snowfall is very heavy, with enough depth to fully cover the rails, it will need clearing before normal trains can run. This is done with snowplows. Countries with predictably heavy snowfall will have this planned in and well managed. It is the rare bouts of heavy snow in countries that normally experience mild winters that catch railway operators out. Then there are points. Points or switches are the moving parts of the rail that allow trains to change tracks. Sections of the rails are swung by point operating equipment, have to be locked in place, and the signalling equipment showing this has happened before trains can pass over them. This is critical to stop trains being derailed. But snow can get into the gap between the switch rail and the stock rail, preventing the switches fully swinging over. Without them fully swinging over, and detected as such, the signalling system will not allow trains to pass over them. As anyone who has made a snowball knows, the more you compact the snow, the harder it gets. This means the issue can worsen as either more snow falls or the points are swung repeatedly. How is this prevented? In the same way that the points are prevented from icing up, by warming them up. Point heating equipment is installed in the form of strips on the rails at points, and when turned on, warms them, thus preventing ice and snow buildup. In some places though, gas burners are used. Another surprising issue with snow that may not immediately come to mind is its effect on trees. Yes, trees. Its added weight can cause tree limbs to break off and drop onto the track, obstructing trains. It may seem a bit niche and unlikely, especially in an area where snowfalls are more of a dusting than a blanket, but it does happen, so I would be remiss not to mention it. So that's snow and ice dealt, but there's one other issue that the cold weather brings that affects track engineers especially: broken rails. Metal contracts in the cold. For steel, this coefficient is approximately 12 millionths per degree Celsius. This means that for every degree Celsius drop in temperature, a 1 metre length of rail contracts by 0.012 millimeters. Now, while 0.012 millimeters per metre per degree Celsius might seem small, over long distances this contraction can add up significantly. For instance, a 1 kilometre of section of rail could contract by 12 millimeters with a 10-degree drop in temperature. The contraction of the rail puts significant stresses on the metal as it goes into higher and higher levels of tension. Cold temperatures also make steel more brittle, meaning it is less able to deform without breaking. This increased brittleness makes the rail more prone to cracking or fracture when it's under stress. A cold rail is both more brittle and under stress. Not a great combination. It is typical to find that when a rail does break, there is already an issue there, some other factor. A rail defect, such as a squat, or track issues, such as voiding at a joint, gives additional stresses at a concentrated area. All the stresses then add up, and the rail cannot take it and breaks. It is not uncommon to see a spate of broken rails during the first cold snap of the year. Right, out of the darkness of winter and into spring. Generally a quieter time of year on the weather front, so I'm going to put it together with autumn and cover some of the weather elements that really occur at any time of the year, before diving into everyone's favourite autumn issue, leaves on the line. Water isn't the railway's best friend most of the time, especially as a track engineer. Lots of it in a short space of time is really bad. The water has got to go somewhere, and if it cannot get away quick enough, then flooding is the result. It can be from a short intense period of rain or prolonged periods of wet weather. Sections of the railway pass through low areas, such as cuttings or tunnels, which means surrounding areas are likely to drain onto the railway. Flooding or lots of water bring a mix of problems. Water and electricity do not mix. Or, as someone mentioned in the comments on another one of my videos, they mix a bit too well. There is a lot of electricity on the railway. While cables are covered by protective outer coatings, they're not really designed to go underwater. Third rail systems are definitely not supposed to be underwater, and when they do, a nice electrified puddle can be the result. Overhead line is not immune either, with the system using the running rails as power returns. Then there is the line-side equipment, such as points operating equipment that sits at or near rail level. Flooding can damage these pieces of equipment, preventing train movement. While trains can run through floodwater, there are limits. Speeds have to be reduced, but at a point, trains cannot run. In the UK, the rule is that normal train speed is fine until the water level reaches the bottom of the rail head. Then speeds are reduced to 5 miles an hour. When the head of the rail is covered, trains must be stopped. From watching some other videos while researching this one, the rules seem very different in other countries, with some pretty epic footage of trains crashing through some floodwaters. Let me know in the comments what your country's rules are. Floodwater brings a risk of damage to the track infrastructure itself. If the floodwater is flowing, this can wash away the track. There is also the fact that once flooded, it is very hard, if not impossible, for the driver to see the state of the track in front of them, or any issues with it. Heavy or continuous rain is also not the best for the many earthworks that are present along the railway. Cuttings or embankments are all at risk of landslips, either onto the railway or from underneath it. Sometimes coming with heavy rain is high winds. Bad enough on their own, high winds can bring trees down, taking down the overhead line with it, or blowing all sorts of weird and wonderful things onto the track. Trampolines seem to be particularly susceptible to a wind-assisted excursion onto the railway line. If the high winds are in combination with a period of wet weather, this heightens the risk of trees coming down, as the ground around their roots becomes loose and less stable. As I touched on earlier, when a tree comes down, there is a risk of it bringing the overhead line down with it, making the whole situation a lot worse. Talking of trees, let's tackle the autumn problem of leaves on the line. If you work on the railway, you've doubtlessly been asked how leaves on the railway line can possibly be a problem. If you commute or regularly travel on a train, you might have asked someone, or yourself, that very question. Well, let's look at why. You can then share this video with all the people who ask you to save yourself having to explain it. Leaves getting on the line are an issue for two main reasons. Firstly, their effect, similar to ice, on the ability of the train wheels to grip the rail. Secondly, it can cause interference with track circuit signalling systems. But it isn't the leaves in their normal form that are the issue. Once leaves drop onto the line, the passing of trains mashes them into a paste-like substance that then sits on the railhead. This is the form of railhead contamination, and it can be hard to shift once it gets on there. This leaf, pulp, paste, when it is on the railhead, forms a layer between the wheel and the rail, an interface that is critical to so many parts of railway engineering. When it comes to grip, the first issue, it can cause the wheel to lose grip leading to trains struggling to pull away from stations, overshooting platforms or signals, or finding it hard to get up steep inclines. Areas with a large amount of overhanging trees, or cuttings with lots of trees, are particularly susceptible. Areas with a history of the issue are known as low adhesion areas, and these may have signs to notify drivers of this. The design differs between areas, but the designs on screen give you an idea. If low adhesion sites are an issue for drivers, our other problem causes issues for signallers. Signallers and signalling systems use train detection systems to detect the presence of a train on a specific section of track. By knowing the location of the trains, the signalling system can then avoid them colliding with each other. Train detection is done in a few ways, but track circuits are the ones that have an issue with leaf fall, so let's focus on them. Track circuit train detection systems work using the train axles to complete a circuit by bridging the two rails. Completing the circuit then shows the section of track as occupied, which won't allow other trains to enter or be routed into that section, but this relies on the transfer of electrical current from the rails to the wheel and back again. Wheel-rail interface. So, if the railhead is covered by a layer of leaf pulp paste and the electrical current is blocked from transferring from the rail to the wheel, or vice versa, then the circuit isn't completed. This then shows the section of track clear of trains, even momentarily, when there is in fact one there. Worryingly, this can allow other trains to be routed into that section and a potential collision, the stuff of signaller and railway staff nightmares. So what can be done, given that engineers cannot stop the leaves dropping from the trees? Firstly, there is removing the trees. This removes the issue, but isn't always the best solution. There is the obvious environmental impact of removing trees, on wildlife for example. Then there is the fact that trees can help, through their roots, stabilise embankments, and the ground in general. They provide shade, which can help keep track temperatures down, while also helping with water management. So whilst removing trees can help in the short term, there is the potential long-term consequences that could impact the area later down the line. Railway and train companies have developed other ways to combat the issue. The timetable of the trains can be adjusted to allow trains to brake earlier and accelerate slower in problem areas without causing delays and disruption. These are sometimes known as leaf fall timetables. Then there is the railhead cleaning. This aims to remove the pulp paste from the railhead. This can be done manually with sprays or rail mounted trolleys, or large sections can be done by specially designed trains, known as railhead treatment trains. These use a variety of solutions or techniques to remove the pulp, such as high pressure water or dry ice. Now, that's 3/4 of the season's done, on to summer. Possibly the season that causes the most worry for railway engineers, especially track engineers. Heat isn't the railway's friend, it's fair to say. Now, I'll preface all this by saying that some countries have dealing with heat down. Typically, it is where the weather is consistently hot and for long periods of time. Similar to the areas that are used to cold weather, it can be prepared for through design and other practices. European railways have the issue of the range of temperatures, as well as the unpredictability of the weather. That means that they have to prepare for such a range of conditions. This means that most of the time they do okay, but the weather at the extreme ends of the scales tends to stretch them. So, where shall we start with the heat? Let's start simple. We have already said that there are a large amount of electrical components on and alongside the track. I think it's fair to say that these components and systems do not do particularly well in the heat. Given the average temperature in some countries, installing cooling system for these components is not often a requirement, viable, or even practical. Until those really, really hot days, when the systems do fail, and everyone asks why weren't they cooled in the first place. The main issue with the hot weather is its effect on the track. In the cold weather section, we touched on how metals contract in the cold. Well, as you can probably guess, it's the opposite in the heat. Metals, and therefore the rails, expand in the heat. As the rails expand, they change from being in tension to being in compression. It's then the job of the clips, base plates, sleepers and ballast to contain these compressive forces and keep the track in place. If you want to know more about the components that make up the track and the role that each of them perform, grab your copy of my Track Component Guide ebook today at the link shown on the screen or in the description below. If you want to know why the track has cant applied to it, you can get your copy of my Guide to Cant ebook. Get your free copy by clicking the link below now. Other track design features help manage the forces from thermal expansion. In welded track, the rails are installed in tension, known as stressing, to increase the temperature at which compressive forces start to build to high levels. Whilst in jointed track, the fish plates joining the rails together are lubricated and the gap between rails set to a certain dimension to allow each rail to expand. The ballast profile, with full beds and shoulders, gives a good mass of the ballast to resist the movement. Ballast is also strongest when consolidated, with the angular stones locking together. Certain sections of track, such as junctions, bridges or tunnels, can be protected with adjustment switches. These allow the rails to change their lengths with the temperature. However, sometimes these design features do not succeed. The compressive forces are very good at finding the weak point in the track construction and exploiting it to move the track, releasing the compressive forces and creating a track buckle. The weak points could be areas of low ballast, wet beds where the ballast isn't fully around the sleepers, areas where the ballast has been disturbed, isn't consolidated and therefore not as strong, sections of rail that are not stressed at the right temperature, or rail joints that do not have wide enough gaps, or the joints aren't lubricated and therefore cannot move. Maintenance teams endeavour to address these issues prior to the summer, or, if they cannot, manage the risk. Watchmen can be sent to sites to monitor them, as well as speed restrictions being put in place. Reducing the speed of trains is the primary mitigation for a number of track issues, as it reduces the forces being exerted on the track. With the rails themselves expanding, other rail components also do. Particularly susceptible are the insulated joints used to separate track circuit sections. These joints have a plastic or resin T-piece between the rail ends that prevent the flow of electricity. As the rails either side of the joint expand, the T-piece becomes compressed. If it is bridged, it will cause the track circuits to both fail, causing trains to be delayed. It could be bridged if there is lipping on the rail ends, which get closer as the rails expand, or it could be a piece of metal swarf or filing that takes advantage of the small gap to cause some mischief. Another area of the rail where the change in length due to the heat can be an issue is the switches. Switch rails are free to expand at the toe. They also have to work with a few other components to undertake their function of allowing trains to change tracks. After installation, signalling engineers set the points up, a term for a full set of switches, points operating equipment and other signalling equipment. This is to ensure that they swing properly and the signalling system can detect their position correctly, all well and good, until the switch rail starts to change length. This can cause issue if they expand too much, stopping the signalling equipment detecting the points correctly. This leads to a points failure. Again, this is most likely on the hottest of days that push everything outside its normal operating window. One of the ways this risk can be mitigated is painting the rails white. This helps in at least some part reflect the sun and reduces the rail temperature. It is standard practice in the UK, for example, to paint switch diamond layouts, as they are particularly susceptible to this type of failure. On the hottest of days, with all the risks adding up, it may be deemed safest to apply a speed restriction to the whole network, known as a blanket speed restriction. As the temperature rises to very high levels, lots of risks come to the fore across large areas, and many infrastructure managers simply don't have the resources to cover all of these risks. Lowering the speeds helps reduce the overall risk. The last issue in the hot weather is the risk of fire. As with wildfires we see across the world, the source of ignition can be varied. Sparks from arcing third rail or other sources on passing trains, as well as overheating equipment, are railway-specific causes. The fires don't have to be within the railway themselves to cause an issue. Fires close to the railway also cause issues, with smoke affecting driver visibility or the risk of the fire spreading simply meaning that trains have to be stopped. Fire can also throw out a tremendous amount of heat. The damage from these fires can be extensive and require a lot of work to rectify. So now you know the ways Mother Nature can bring the railway to a halt, and some of the ways railway engineers design and maintain the railway to keep trains moving. Think I've missed any? Drop them in the comments below. Please do hit that like button, don't forget to subscribe, and check out some of my other videos linked on screen now.